All right, let's get back to our seats. All right. Next is Atila Neves. He's not a model, he's the actual engineer. Doesn't have anyone representing him. He's a good-looking Brazilian.
Why, thank you.
Atila is going to talk about case studies in simplifying code with compile time reflection. I remember having read the proposal. It was like very intriguing. And well, we had to invite him here, so take it from here.
Thanks. So, like you said, my name is Atila Neves. I started writing D around last year, and because I'm a little bit crazy and stupid, my first 2 projects had to do with compile time reflection, because easy is boring. So what happened was last year I was watching DConf videos, and compile time reflection got mentioned, but I didn't really understand what it was good for, how to use it, or any of those good things. So I basically did a presentation I wish would have happened last year when I was watching. So I found this quote somewhere on the internet once when I was watching someone else's presentation. I tried looking for the original slide, but my Google foo was weak. In any case, this is all about what compile time reflection is for me. You know, writing code to write code to write code, because why would I do that? I'm lazy. So the talk, like I said before, is like what compile time reflection is, what you can achieve with it, the advantages you can have using it over runtime reflection, not that we have a choice in D anyway, and the practical use case scenarios from real projects, so code I wrote that made use of it, unit threaded and serialed. The first one is a unit testing library, and the second one is a serialization library. Yeah, D has unit tests, but there's a few things I need from a unit testing framework that D doesn't have. The built one is good for small projects, I think, but not for the kind of things I want to do. And I was doing some serialization as well, and I could have used something else, but it was more fun writing my own. Also, again, it does a few things that I need that I couldn't find anywhere else. And as I mentioned, kind of touched on before, there's not that much information, I don't think, in terms of documentation, in terms of what you can do and what you can achieve. If you go on dlang.org, the examples that you find there mostly use pragma to print things out or write ln, and that's cute, but you know, what's the use? So I tried using it in real life. So what is reflection? It's the ability to inspect and modify a program. You see inside classes or how many parameters a function has, that kind of thing. List of members and methods of a class. You can even add code whilst you're reflecting. Now, normally, in other languages, it's done at runtime. You know, languages like Java, C# or scripting languages like Python. I'm not going to try to say that D is the only one that has compile time reflection. I'm not going to try to make a list of languages that have it, because I'm sure somebody on the internet would correct me. Now, the only advantage I can see to runtime reflection is you can even call methods that you don't know exist at compile time. You get a call awesome method thing that you find out, and you can call it. Now, indeed, this is all available at compile time. __ traits allows your programs to get information that's internal to the compiler. So the compiler sparse your program, and it can make that information available to you. There's several of those traits, and they do a bunch of cool things. The other thing that D has is in the standard library, SCD traits, you have a bunch of templates that can inspect compile time information for you and can give you good information. The only problem I have is I never know where to find what. I usually have 2 tabs open, one on double_ traits and the other on phobos, because I never really remember where is the functionality to do what. And all of this works really well with D's compile time function execution, static if, and mixin. And it's hard to kind of get why. When I read the D programming language book and I read about mixin, it kind of seemed useless to me. OK, I can give you a string and you can compile it, but I could just type it myself. Until I realized that the phrase known at compile time doesn't mean a literal string, because we can calculate strings and modify them and append to them at compile time. And that's where things get really, really useful and powerful. So what are the tools available? The bread and butter, the one that you're going to go to first, is going to be the traits all members. So T there is any type that you have, any type that you've written. It can even be a module, actually. You can list all the members in the module. You can do a bunch of stuff. And what it does is it returns a tuple of strings. And like I said before, yes, you can print them, that's cute, but show me something else. So the example here is very basic, right? I mean, you got your standard import std, stdio. You've got struct that's only got an integer and a string. They're called ins because I'm lazy. And then in main, you do a for each over that tuple, saying for each member in it, I'm going to call it m, write ln, m is m. And the output's there. It just says m is I, m is s, the names of the members in the struct. And you can print them out. That's cool. That can help you to debug. But it doesn't really do anything that useful. But like I said before, mixin and the traits that says get member, because now you can pass that string to traits get member. That's what makes it useful. You can actually get that from a value, or at least generate code to get that from a value at runtime. And there's other useful traits and templates as well that you should look into for more complicated things. But all members is basically where you're going to start. Here's a more complicated example. It's still a toy example, because putting real examples up is going to be a lot more complicated. So we have 3 structs there. One of them has a string and an integer. The other has a Boolean and a string, but the string's in the second position instead of the first. And then you have this bash struct with only an integer and no strings. And I wrote here a get string function that can run at compile time that takes any t. And then it does, again, a traits all members. For each one of those members, it gets the value from the value. So it generates the code to get that at runtime, depending on the object you pass to it afterwards. And then if it's a string, you return it. And if there are no strings in any of those members, it falls through and returns an empty string. So if I have this main function here, the output's going to be the string of foo struct is foo, because that's the value that I'm passing at runtime. So what it's doing is it's just trying to find me any string in that struct and returns the first one. In the second one, the string's in the second position, but it finds it anyway and prints out bar. And in the case of the third one, because my code just returns an empty string, it goes string of bash struct is nothing, because there's nothing to print. So this is already a slightly more convoluted example, but again, not entirely useful. Now, I started using this because I'd written a unit testing library in C++11. And the way it came about was I used actually several unit test frameworks at work before. We had an internal Syscall tool before. Then we used CPP check, and in the end, a colleague of mine just wrote one of his own. But the thing is, it always kind of annoyed me that we needed preprocessor macros and boilerplate to do the checking and registration of the test. You always had to say, here's my test, and also please register it with the framework so it gets run at runtime afterwards. So I needed a testing framework for a personal project of mine, which is a game I wrote called Gravistar. And I was just learning about C++11 and async at the time, and I kind of wanted to put that into the game. And then I sat down to work on the game, and I ended up just writing a unit test framework for the whole day and not touching the game code at all. And so I used what I liked about the framework we had at work. And I still had pet peeves about it, I wasn't entirely happy with the result because I was so bothered by the required boilerplate, and I hate boilerplate. I hate having to type things over and over again. I just want to get my job done instead of typing things I shouldn't need to. And I mean, to paraphrase the old adage, I had a problem. I tried to solve it with C macros. Now I have 2 problems. So this is an example of the kind of thing that bothered me. Okay, so we have this macro called register test, and it takes a path because you can organize your tests in a path-like structure, like a directory, which doesn't, of course, need to be the same as the actual directories because you don't really know where your files are. And it just assigns this dummy Boolean variable to the test case factory saying, please register this thing here. And then I write my structs. I derive it from a test case class. And I write the actual test, and then I have to do this register test macro. So this kind of bothered me because I'm repeating the name of the class by declaring it, and then I have to put it down there. I have to always figure out what path I'm going to register it under logically. I can't just pick it up from the file system. And had I consulted how Google Tests does this, I would have realized there's an easier way to do this. But I think that's kind of fortunate in the same way because that made me write the library I ended up writing. So Google Tests is a macro trick that I learned afterwards, but still a macro, still got problems. And around the same time, I learned about D, so I figured, what about that compile time reflection stuff? Can I use that? Can I use that instead of registering my test myself? And the answer is yes. So I decided to see how much easier it would be in D, and so I wrote a D version of the library. So I realized at a certain point that test discovery, so the test registration problem, is essentially compile time. At no point in time do you want to define what tests constitute your set at runtime. That doesn't really happen. You might want to run a subset of those at runtime and pass those as arguments, but the whole set of existing tests is a compile time thing. You know that at compile time. You're not going to change it at runtime. So the driving design principle was the least amount of boilerplate possible because I don't like writing code. I want the compiler to write the code for me, so could I do that? The main issue I had to solve is returning all the test cases in a list of modules that is known at compile time. And the secondary issue is now that I know which tests exist, how do I translate this into runtime code that's going to instantiate them and run them? So here's a very simplified example. The real code has a bunch of corner cases and things it has to deal with, so this is idealized code. It would work, but it wouldn't work in every single case. It's a bit longer, and I've got the output of things that's going to happen here. So I define an interface called test case that's only got one method called test that you need to implement. Then there's just a test class that's there. The only reason it's there is so it can be discovered and run. And there's another test class that is a class that happens to be in this module that I don't want to be a test case. I don't want to register it. It doesn't derive from test case. It doesn't implement a test method or anything like that. So the test I'm using here in the eponymous template is something a test class? Is it a class? And does it have a member called test? That's pretty much it. It's not very complex, but it kind of works. And again, this example is very simple. So anything else that has a test method that isn't derived from a test case would pass that enum, but would have problems that I'll talk about later on if you did that. So I've got this function here called get test classes, and it returns an array of strings. Basically, I just want to know the test class names. I want to know what is the list of test classes in this module. Normally, you would do this from a different module, but just to keep the slide short, I've put the test case and the function that actually finds it in the same module. So we see our old friend all members. So we do a for each over that. And if it's a test class, which we know at compile time, and we're using a template for that, then we add to that array, and then we just return the thing. And of course, I'm using the fully qualified name there because at the bottom and in the main function, what we have is for each of the test classes that you've discovered, by the way, I want to create it. And fortunately for us, D has an object factory, so we never have to write one again. You just need to pass the name of the class in, and you're going to get an instance. And also, fortunately for us, the D cast, in this case, works like C++ dynamic cast, which means if by chance that object isn't a child of test case, you'll get a null, which is why I said before, that test really isn't very good, because you could define a test method, but if the class doesn't implement the test case interface, the cast in the main function would fail, and you'd get a null. And then you run test case test. So I included the output of the for each get members in this module, because you get a bunch of things. Some of them you'd expect, some of them I wouldn't have. For example, std gets printed out. I don't know why, but it's in there. But after you loop over these, you check to see if any of them is a test class. And in this simple example, the only thing that does pass out test is our test class thing. But that's the output you'd get from that for each. That's all the strings you get back from it. And then when you call get test classes in main, it returns an array which only has one string in it because we've only got one test case, and then it does a test in each one. So the output from this program is test class.test because that's what's written up above in the test method. That slide's a bit dense, but I didn't know how to make it any simpler. And again, like I said, in real life, it's a lot more complicated. But what about functions? I mean, functions require a lot less boilerplate. I don't have to declare a class at all. I don't have to make it derived from anything else. I'll just go void test something. Can I please schedule this to be run? And the answer is yes. The functions can be discovered just like the classes. There's no difference. You just reflect on the module. You get a list of members. And now you just have to write a different template, which gets you a Boolean saying, is this a test function or not? In my case, what I did was I considered anything that starts with the word test and then an uppercase letter, so in camel case, anything like that is a test function. Anything that isn't like that isn't. But my problem, and I had to scratch my head quite a while with this problem, is discovering the functions was easy. Now, how do I call them at runtime? Because what I was doing with the classes is just taking a string and then calling object factory, creating them at runtime, and then running them. So with the functions, I basically did the same thing. I wrote a class that wraps the function. So you discover the function at compile time. You generate the code to wrap it in a function test case class. And then you create that guy there. And it knows how to call the function that it's wrapping. And then, of course, you need a create test case function. You can't just use object factory directly because you don't have a name of that class. That class is the same class for all the test functions. And I have a different function that knows how to create an instance of each one. And things work. You dispatch at runtime, and you get the right test being called. But of course, compile time reflection can do a lot more with EDAs, which are user-defined attributes. A lot of people call them annotations because that's what they're called in Java. In D, they're only compile time, and it's the expression that we attach to any declaration. The expression is usually enum or a struct, but not necessarily. You can attach values as well, an int, a string, anything else. And it can also be inspected with compile time reflection, just like anything else. And now you can generate code based on what's annotated. You can use static if to say, if you have this certain kind of UDA, do this. If you don't, do that. You can even inspect the UDA itself, because if it's a value, it has maybe interesting information in it, which happens. And in unit threaded, I have a few of them. I have the @unitTest attribute. That means I can decorate anything with this and say this is actually unit test, so please schedule it. So if you have a function that's called foobar and you stick unit test on it, it will also be scheduled for execution. Or maybe you have a function that's called test something, but you don't want it to run. So you can use don't test. You stick it on it, it won't run. The other way you can do that, of course, is making the function private, because if it's private to the module, any other module, which is the module that's actually trying to reflect, can't see it. So you won't be able to run it from there either. And my favorite ones are the last three, single-threaded. So my library runs a test in threads by default. But under certain circumstances, especially if your function's a changing global state, which we all know we shouldn't do, but sometimes you can't escape from, especially if maybe you're calling C code and you didn't write the other code. You stick that single-threaded in a function, and then all those test cases in that module get run in one single thread, but only for that module. So I like the way that you can isolate that too. Hidden tests, you can hide a test temporarily because it's a bug. You don't want to fix it now. You put it in a database. You'll get back to it later. Should fail is also called, that means a test passes if it throws an exception. So if you discover a bug and you don't want this thing to be read in continuous integration, you stick a should fail on it, and then you will know when you fix it. You can't forget to fix it, right? Because hidden tests, you can hide it under the carpet. Should fail, you can't. If you fix it, the test will fail, so you know you have to go at least remove that thing from there. And this is what it looks like if you write a module that has a few tests in it. There's just a test function up there that just asserts a 3 and 2 is 5. I can stick the unit testing in another function with a weird name that will still get scheduled and run. That thing will never throw an exception because it says don't test. And the one below passes because it throws an exception. The should fail UDA takes a string because it's usually going to be a bug ID. That's the whole point for it. But it's useful to know why the test should fail. Just sticking should fail for it isn't very good. So your coworkers can come on afterwards and know why it is that you put that there in the first place. And this is an example of using unit threaded to run your tests. So you just have to import a module from unit threaded. And then it has some arguments, so it does some parsing for you, so you can control whether or not the tests do run in threads or not. You can run the tests in random order. It will give you a seed that you can use to rerun those tests in the same order that just failed if it happened to fail. And you have to pass in the modules that you want to be reflected. Now notice that I'm passing the modules in as strings, okay? You might find that weird, but the reason for that is to, again, eliminate boilerplate. Because if they're not strings, which you can do as well, by the way, I need to import all of those. So for every test I have in that list, I have to go import test.fill.normal, import test.fill whatever, so the symbol is visible and I can pass it as a compile time parameter. Since I don't want to do that because, as I said before, I'm lazy, I just pass the strings. So what I do is when the string gets passed on, I do a mix-in import the string, and now it's visible there, and that's the place where it's going to be used anyway. So it's a lot easier to use. The only problem, of course, here is that the compiler, for security reasons, can't just go willy-nilly looking at your file system. And since the packages are directories, I can't just reflect on a package, right? I can't discover what modules exist in it. So unfortunately, you do have to specify the list of modules. So the module themselves, you pass it in, whatever's in there you'll find. But the list of modules is something that you need to manually do. Now, this could be a part of the build system. You can have a script to automatically do this for you with dependency management. And I wrote a program, of course, because I wasn't going to keep doing this myself either. That scans the directories at runtime, generates this file for you, and then you can run it afterwards. That program's called dtest, and it can also use RDMD, which it actually does by default, to run that file. So you can just go dtest, and if your test by default, it looks in the directory called tests. It generates that file and then runs it. So you don't need to do anything. So I was kind of going for the same thing that Go test lets you do. So it's zero configuration, zero boilerplate, just run dtest. Of course, it'll take slightly longer because it needs to generate the file, then compile it, then run it. OK, so serialization in different languages, because that's the unit testing part done. I also had to write serialization for my game in C++. And I kind of based it on stuff we had at work as well, which is very similar to what the Boost serialization library does, because there's not really that many ways you can do it right. I think Boost does it right too. The good thing about it is that you don't need to have to write a function to serialize and deserialize. You don't have to write nearly the same code with the same members twice. You write one function and it does both directions for you. And it could even do something else, like, for example, count the number of bytes. Maybe you need to know ahead of time how big the stream is going to be for some reasons. So the way you'd use this is you have a myStruct here, it has an integer, it has a string. And in C++, you have to, for each member in your struct, you need to write the code to serialize it, because or else, how are you going to do it? So it's a lot of boilerplate. And of course, as that struct is big and has a lot of members, there's a lot of things. You have to repeat the declaration, right? You declare the struct, you declare the members, and then afterwards, for each one of them, you need to go and write the code that does this. And because I was going for the Qt name of serial, I thought that the function that actually does serialization for, of course, templated for any member, I called it grain. So you go serial.grain_myInt, serial.grain_myString, and now you can deserialize, serialize, either way, you're done. And the way you use it is in the bottom there. You instantiate the serializer, because it's going to go from struct to bytes. Then you stick it in the serializer, and then you have your bytes, and that's how you use it. Now, the difference is that in languages like Java or Python, you don't need to do all that boilerplate, right? They have runtime reflection. So you don't need to write any of that. Pickle just does it for you. Normal Java serialization just does it for you. But you pay a price, because you're doing it at runtime. So they need to figure out what's going on at runtime. And I've seen a bunch of Java libraries trying to be fast because of this problem. And one of my colleagues is a big Java developer, and he says some people even write code to generate Java bytecode at runtime and stick it in the JVM so that it's not slow. Now, that isn't easy, OK? And also, you're paying the price because when you generate the bytecode, the program takes a bit longer to start. So these are all problems. You can have convenience and it's slow, or you can do C++. It's inconvenient, but it's fast. But D, we can use code generation compile time and have our cake and eat it too. Now, the D version of my library kind of looks like this. The struct is pretty much the same. You have an integer and you have a string. And the way you use it is nearly the same, except instead of the C++ overloaded left shift operator, you have equals append, or append equals, depending how you want to read that. And then that's it. There's no more code. There's no boilerplate. I didn't write anything, and I can now assert that the bytes that are in there are those numbers there. The reason why is those first 4 bytes are the integer, because it's 32 bits. And then in the string, by default, what it does is it puts a 16-bit integer telling you what the size of the string is, and then the individual characters, which I wrote like that so you can see that's the exact same string that you put in. And then I can take those bytes, put it in the deserializer, and then assert that it's actually the same as the struct I got before. The values are the same. It all works. I have to write no code. This is great. Fantastic. However, real life is messy and doesn't work like that. I mean, how many times are you going to write a struct that has an integer and a string, and that's going to be used for anything even remotely useful? Hardly ever. Okay? So what happened is, after I'd written that library, I was trying to write an MQTT broker because a colleague of mine who's crazy about Go challenged me, saying that his MQTT broker, written in Go, had to be the fastest one in the world because that's what Go is good at. To which I said, "You want to bet?" And of course, I beat him. Had he bothered to actually measure timings, he would have seen that the C implementation we were using was already faster than his Go implementation anyway. But I think it's fortunate that he never did, because that meant he was able to challenge me, and then I ended up writing this code, which I wouldn't have done if he'd bothered measuring in the first place. Right, so what happens is in a real project, in real life, you need custom serialization. It's a fact of life, pretty much. So that cutesy example I just showed is not going to work. You're going to have to write some extra code. But often, for the most part, the standard behavior, that thing I just showed that does it magically for you, works. Okay, it's good enough. So how can I combine those two? And what happens as well is a lot of data you have in a struct isn't supposed to be serialized, maybe. Or it might require logic to do so. It's not just something you can just take and put in. It depends on other values, maybe. And there's no way you can't write that code because it's logic. So you have to write the code, because the compiler isn't going to guess for you. And network protocols as well, nearly always, have sub-byte data encoded into bits. I mean, I work at a networking company. MQTT is a binary protocol. That's the kind of thing I deal with. That's the kind of thing that's going to be hard to do. And I was just tired of bit twiddling over and over again, left shift, right shift, or it's just a massive, massive pain. So even though I wrote that library, and I'm the author, even though I knew that that thing existed, and I wrote it to not require boilerplate, at the end of the day, when I started writing the MQTT broker, I was an idiot and kept on doing custom serialization and back and forth to make things worse. Okay? I wasn't just writing one function, I was writing two. One to serialize, one to deserialize, because I couldn't figure out yet at that time how I was going to do that with only one function. So I negated the benefits of my own library and didn't even use it. I was basically doing the same thing I was doing in C++, but in D. And I thought to myself, well, this is silly. So let's fix it, and I did. So instead, what I ended up going for is using UDAs and the D concept of post-split. So I stole the name from the post-split constructor, and I stole the idea. The idea here is that, for the most part, the default thing that I'd written before is OK. So let's do that. Okay? And now, if necessary, we can fix things after the fact. So we post-split. And for the most part, I wanted to use declarative code. I don't want to write code. Let the compiler do it for me. And well, actually, it just says that there in the last line. I want to intervene when it's necessary, not in any other time. So here is the header of an actual MQTT packet. All of them begin with this. Okay. So as usual, things are encoded in bits. It's not nice and fuzzy. You have 4 bits of the message type. Then you have 2 bits of indicative as duplicated or not. Oh, sorry. 1 bit for that. Quality service level and 2 bits, and then the retained bit, and then the remaining length. Now, the thing about the remaining length thing here is it's not even just 1 byte. There's an actual semi-complicated algorithm to calculate what the length actually is. It's only 1 byte if the length is less than or equal to 127. If it's any other value, that means there's other bytes to follow. And there might be, I think, up to 4 bytes because it supports really, really big packets. So that needs logic right there. I mean, if you look at the spec, there's an algorithm in it to calculate the length based on the value that's there. So how many bytes and all of that kind of thing. So this isn't going to fly, not with the thing I showed before. So how do we fix this now in the current version of the library? So this is the D code that's actually in the MQTT broker. This is on GitHub. You can go check it out. So I have an enum. These are the message types that you see in the first 4 bits. So I just declared a few of them there. And the struct declaration for that header is the one that you see there. So what I did was I annotated all of those data members. The first one is just saying, use 4 bits for this. And then it has the enum. And then, of course, the other ones are just as readable. Use 1 bit, 2 bits, 1 bit. And then, nearly my favorite part here, it says, do not serialize, do not touch this. I do not want you, library, to touch this. The remaining size is not to be touched, and it doesn't. But you'll see that it does work here, and I'll show how in the next slide. So how do you use it? I instantiate a serializer. I say, please append this struct, which I constructed on the fly there, and I said, the type is publish, the dup flag is true, the quality of service level is 2, retain is false, and the size is 5. And then I'm having assert there because this will actually happen in real life. You have the serialized header as you would want it to be, as you would have written if you bit twiddled yourself, except you didn't have to. There's no ands. This is nearly the entirety of the code already. There's only one thing missing that's in the next slide. But that's all you have to do. You declare the struct, you say serialize this, and of course, it works in the opposite direction as well. And it happens. It just works. Now, you'll notice that there's a 5 there, right? That's the 5 that I said was the remaining size. But I told it to not serialize. How does that work? Like this. So like I said before, the post-split thing kicks in after. So what happens is the library looks at this, does compile time reflection, says, oh, I see you have a type here, and you want me to store that in 4 bits? Not a problem. I'll do that for you. Then it moves on and stores 1, 2, and 1 bits, and of course, all of that takes 1 byte. Then it looks at the remaining size and says, oh, you have a no serial thing here. I'm not touching this. And it doesn't. But what does happen afterwards, it uses compile time reflection to see if your struct has a function called post-split. And if it does, it calls it. So this is the actual code. There's some other code in the bottom for other things, but this is from the actual example. And I'm using the template constraints here so that in one case I only do serialization, and in the other case I do deserialization. The reason why I did this is because those functions that are called that are in the private section, set remaining size and get remaining size, I did not write. And I didn't write because I just took them verbatim from the MQTT spec, changed the syntax to BD, and it just worked. I didn't have to debug this. They gave me the algorithm. It's possible that I could rewrite this so I could do this in both directions, but I decided that was too much work and I didn't see the point. But normally, you would have one post-split function, and it would do both. You could just say, grain this, or grain that, or don't. And we'll see an example, a more complicated example from the same program that does that. So this is the actual declaration in my code of the MQTT connect function. And I picked it because it's the longest one in the spec, because it has a bunch of stuff in it. And forget the post-split for now. So what we do is we declare MQTT fix header, which is the struct I just showed you. I don't have to handle it anymore. Why? Because it recurses, right? When it sees that fix header, it's like, oh, how do I serialize this? I already have the code. So it takes the code it already generated before. Then there's a string. It does what it has to do. Then there's the version. It does what it has to do. Then there's a bunch of flags in there. One of them actually is 2 bits, but there's a bunch of values, so I'm just telling it to store in that many bits. And then another 2 values, nothing special there. And then those last 4, it says, don't handle this because you don't know how to, and I do. Why? Because I need logic. Those things might or might not be there in the packet. And those flags that you see before are what control if those fields are there or not in the packet. Which means for me to know if I have to serialize or deserialize this, I need logic. The compiler isn't going to know that for me. The compiler doesn't know the semantics of that thing just because I gave it a name that makes sense. So I write the smallest possible amount of code that will make this work. And that code is that post-split function there. It says, because I know this only runs at the end, all of these other things have been handled, and those other the possibility of there being something or not is at the very end. So if that bit called has will is set, then please handle the will topic and the will message, because they'll be there. Either they'll be there in the packet, or I want to put them in the packet. Either way, it doesn't matter. It does both directions. If the has username bit is set, please handle the username. And if has password is set, please handle the password. That's literally all the code that needs to be written, and it works. Declare everything you need. The compiler generates the code for you. Worry only about the logic you have to write, because the compiler isn't an AI that's going to write it for you. Okay? Now, the cool thing about this is I can do compile time error detection as well, because since everything happens at compile time, I can force users of the library that don't make any sense to fail to compile, which is, of course, a lot better than it failing at runtime. So in that bits thing there that you see, what if I put 9 bits and I try to store it in a byte? That doesn't work. So we check for that. And if you try to compile that program, you will get that error message at the bottom. It says that, and of course, it tells you what the struct is. It tells you what the field is that you tried. It's 8-bit longs, which is not enough to store bits 9. So that field needs to be bigger. That bits thing as well, if I'm not mistaken, only supports up to 32 bits. So if you try using any number more than that, it will also fail at compile time. Of course, if you try using a negative number or 0, that won't work either. Now, what are the advantages of compile time reflection over runtime? Because a lot of these things you could have done in Java just as well, except in D it happens at compile time. One of them is efficiency. You can inline aggressively. You wouldn't be able to otherwise. All that code that's generated, there's no virtual function calls. There's nothing like that. The reflection itself is in the compile time. So you don't pay a price at runtime to have the reflection happen because some object came over the network or something like that. And also correctness. Like I showed before with the bit struct, I can check for things at compile time. I can do a static assert and say, no, and by the way, this is why. And since static assert is so helpful as to let us pass a string, we can format that string and give a very concise and clear error message to the user about what's going on, and they can figure out what's going on from there. So incorrect code doesn't even compile. And the privacy of members is respected. Because in Java, one common question in Stack Overflow is, how can I stop people calling my private methods if they reflect at runtime? The answer is you can't. How could you? If something's private or not is something the compiler knows, is determined at compile time. After you've got the bytecode, you can do whatever you want. You can't in D. You make something private, I can't touch it from another module, which is good. That's what we want. Now, touching on a subject that 2 other talks have already mentioned today, there are problems with this, though. It's not all fun and games. Sometimes somebody does lose an eye. In this case, I probably lost about 3. Now, it's really hard to debug, OK? I used program message a lot. I had no idea what was going on a lot of the time, and I just print this out. I don't know what it is. The compiler just fails, and you don't know why, and you just print out the intermediate steps. I found there was some helpful traits missing. I should probably maybe write them and try to get them into Phobos after what Andre said this morning. But yeah, I found that, for example, just checking to see if something has an attribute doesn't exist. So it was kind of complicated for me to just say, does it have this? Traits as well, the API isn't really that consistent, I guess. I mean, there's probably good reasons for why it works the way it does. But I never know what that thing returns depending on which traits I'm using. If it's get member, all members. Sometimes it returns strings. Sometimes it's symbols. Sometimes it's, I have no idea what it is. Sometimes I have to use alias because there's a type. Sometimes I can use enum. I basically try enum until it doesn't compile, and then I try alias. It probably will, but you never know. And if you don't know, program message print, what is this? I don't know. I found that I repeated myself a lot in ways I never would have done if I was writing runtime code. And I found it hard to refactor. Every time I tried refactoring some common functionality out, the compiler would complain, and I didn't know why it was failing. I don't have any concrete examples now, but even as recently, when I knew more about D, because remember, these were my first 2 D projects as well. Now that I know more about D, I managed to do things that I didn't before, but sometimes I still keep repeating myself because I don't actually know how to do it any better, and it just fails. I might ask about one of them on the forums. I need to go find the code where it is. Basically, I just need to find repetition. So I find it hard to refactor myself. It can be really hard to reason about what runs at compile time and what runs at runtime in the same code. You look at the code and you don't really know what's running when. In several situations, I was trying to write compile time code, and the compiler says, I don't know what this value is at compile time. What are you talking about? Because I didn't know what was running when. And in fact, I did this talk about a month ago to my work colleagues as a dry run. And somebody asked me questions about the actual code and pointed to lines. And he said, when does that get run? And I went, I don't actually know. And I had to think about it for a while, and I do now. But it's not something that comes naturally or easily. And for each on tuples is the worst offender ever. Oh, I'll unroll this for you. OK, thanks. I had no idea you did that. I use traits compiles a lot, which turned out to be a mistake because it's a massively blunt instrument that will kill everything in its path. But you don't realize that until things go wrong. So what I was doing is, for the serialization, I was looping over the members. And of course, if you have a class or something like that, you have members that are functions. You're not going to try to serialize that. So how did I determine whether or not I could? I naively said, if it compiles, then please generate this code. Unfortunately, this also means it could not compile for any number of other reasons. So I introduced a bug once, and then the thing didn't serialize, and I didn't know why. And I was basically complaining, banging my hands on the table, like, you stupid compiler, why aren't you telling me why? And then I realized, because I told it to shut up. I said, if it compiles, try. It doesn't, so it didn't. It didn't tell me why, because it didn't ask. So I changed the code eventually. And of course, you can imagine how hard this was to find. And once I did, I said, look, if it doesn't compile, try anyway so I can get the error message and figure out what's going on. Because if I had the error message, this would have been super simple to fix. But I told it to shut up, so I didn't know. And of course, as we all know, writing compile-time code is a lot harder than writing runtime code. Even trying to explain this stuff for people who aren't used to it is hard. So my brain hurt a lot. And again, because I'm an idiot, that was my first D project. And I was like, I don't know what I'm doing, like that dog in the meme. And it's also impossible to reflect on packages since packages are directories. I understand why, but it's still annoying when I have to list all the modules I want to reflect on anyway. But I understand why. And since then, I've actually used compile-time reflection and other things that are pretty cool. I nearly thought of talking about them in the talk instead of this stuff because it's cooler. But I did say that I was going to talk about this, so I did. So maybe next year? I don't know. And of course, obligatory meme, this exhibit saying that if you like metaprogramming, you put a compiler in your compiler so you can compile while you compile, which is true. And there's a bunch of links, traits, attributes, all that kind of good stuff, and the links to the projects I've talked about here. If you want to check out the code, go look at it, complain at me, yell at me, pull requests, whatever you want. And that's me, so I'll take any questions.
Many thanks, Atila. Okay, questions.
Okay, I have one question, one comment. Starting with a question. The case where you have used the class wrappers to call functions, was there any reason why you didn't consider just like building an associative array of like test names to kind of function handlers and using that instead of generating like class?
I don't think I did consider that. That probably would work. I'd have to look at the code and kind of figure out. Maybe my mind was already set because I already had the test classes before. So I kind of made the functions fit into that scheme instead of the other way around. The thing is as well, I didn't just use it for that. Back when we didn't have the traits to find the unit test, the actual unit test blocks from D, what I did was to figure out, I wanted to run those unit test blocks too. And what I did was I used the module info instead, and that kind of just fit together more naturally at the time. It's possible that now I could refactor it and use it simpler, but right now I can't tell you.
Yeah, another thing is that you have mentioned that it is not possible to reflect upon packages, but it is not actually true. You can reflect upon packages that have been imported already.
Right.
So kind of the place where you have been like listing the sample output of all members for a model, I think you have mentioned that there are like std and
right.
and like why they are there. And the answer is that all members for a model actually list all packages and models that has been imported.
Okay.
So it is quite possible to simply like import all test models you want and just like supply a top-level package name for all those models and reflect upon this to find everything recursively.
So you're saying if I import SCD something, I could go reflect an SCD and find out every module in SCD?
Yeah, what modules was actually imported.
But I don't want that. I want every module that exists.
That's a different thing.
Right, but what I want is to find out everything that's here.
It's different kind of reflection, kind of. If you actually import that, then it is possible to reflect upon it, just like stating that it is close to the same elimination of boilerplate.
Right, right.
So like instead of like mentioning strings for all modules, you can just import those and then just supply a single like top-level package that hosts those to do actual reflection. That could have been an alternative.
Right. Okay. But again, well, what I want is find me all the tests in here, and I don't care how.
Regarding post-split, I've always been kind of uneasy about post-split because I couldn't figure out what it was good for other than a reference counting type. And I want to congratulate you on finding a legitimate use for post-split.
Thanks.
I think you've probably saved it.
Well, I stole the idea and the name, right? And it just worked. Because the thing is, I don't want to do these things by myself. So the first thing I did wasn't even post-split. It was serialize, which means if this function is defined, I'll call it instead. right? But I don't. And then what I did was inside that I would say, well, for this member do this, for this member do that. But I don't want to do that. For the most part, the standard thing's okay. I just want to fix stuff at the end. So if you hadn't invented the concept of post-split for destructs anyway, I wouldn't have had that idea. So thanks.
Questions? All right. Let's thank him again. Thanks, Atila.
Thanks.
Okay, awesome. So, couple of announcements. We're gearing for the destruction session at 4:30. Walter and I are going to be in the front, ready to take any abuse you may throw at us. And another announcement, the t-shirts are ready. They are awesome. And we're going to distribute them after the destruction session because I may have a word in that, depending on what you ask and say. All right, so see you again at 4:30.